This lecture is about the kinematic equations, which are some of the most important and central equations in all of physics. They come up again and again in many different topics. Before we go in, I'm going to start with the definition of kinematics itself. So kinematics is the branch of physics concerned with the motion of objects without reference to the forces which cause the motion. What this means in everyday language is that kinematics is the way that we predict different parts of the motion of an object only using other parts of the motion. We don't need to know anything about what type of object it is or what forces are acting on it to predict its motion. We just need those other parts. So the main idea is that any object in the universe, no matter what it is, if it's an asteroid in outer space, if it's a toy here on Earth, if it's anything in between those things, if we can understand just a few small parts of its motion, we'll be able to predict the rest of its motion without any other information about what it's doing or what forces are acting on it. So these are the equations and the kinematic variables. You can see that there are 5 variables that the kinematic equations connect: displacement, initial velocity, final velocity, acceleration, and time. I've written the variables for each and the unit that we use to measure each in the boxes up here. If you get any values that are given in different units than what's on the list above, it's best to convert the units back to the units shown here. That's usually the easiest way of solving the problem, to convert everything back to these base units specifically. The 4 kinematic equations are written above my head. Each kinematic equation connects 4 of the 5 kinematic variables. So that means that you're going to have to select different equations to use based on the variables that you have and the variable that you're looking for. We're going to talk about that a lot in this video. There are 3 steps to solving a kinematics problem. I'm going to have you copy these steps down. I'm not going to read through all of them right now. I'm just going to emphasize one really important thing in step 2. This is a really central idea in kinematics. Kinematic equations can only be used if the acceleration is constant over the motion they are predicting. Nothing else about the object being analyzed has to be constant. The position doesn't have to be constant, the velocity doesn't have to be constant, the velocity can change from positive to negative, the position can change from positive to negative. The only rule that will prevent you from using a kinematics equation is if the acceleration is not staying constant. That's the only time when you cannot use a kinematics equation. And even then, there are often solutions available. If the object accelerates at different rates at different times, you just have to split the problem up into multiple parts where each part has a constant acceleration. I'll show you how to do that a little later in this video. So I'm going to run you through these 3 steps and show you how to solve them. This is example number 1, the first kinematic problem. A dog is running and starts to get faster at 2 meters per second for 3 seconds. If the dog covers 20 meters over this time, what velocity did it start with? Okay, so step number 1 is to define one direction as being positive and the other as being negative, and it doesn't matter which direction we choose as long as we keep that consistent through each variable in the problem. So I'm going to consider the direction of the dog's motion as being positive, and I'm going to kind of arbitrarily define that as being to the right. So the dog is moving to the right and positive. I just kind of arbitrarily chose that. Step number 2 is to check and see if you have more than one acceleration in your problem, and if you do, you're going to have to split the problem up into multiple sections. And here I can see that I don't have more than one acceleration, it's just that 2 meters per second. So I'm going to skip step 2 because I don't have more than one acceleration. Step number 3 is to use a Suvat table and the guess method to identify the correct equation and solve the problem. If you have 3 kinematics variables, you can solve for the missing variable. This is what a Suvat table looks like. Suvat just stands for every variable in the kinematics equations: displacement, initial velocity, final velocity, acceleration, and time. So I make this table to start filling in any data that I'm given from the problem. And the rule is that if you have at least 3 kinematic variables, you can always use them to solve for the other 2. So I'm going to start to fill this in and see if I can solve for the missing kinematic variable. So I can see right away that my acceleration is 2 meters per second. I'm going to consider that to be positive because the acceleration must be happening in the same direction as the dog's velocity, because the dog's getting faster and faster. So because that acceleration is happening in that same positive direction, I'm also going to consider it to be positive. Just a reminder, I'm not calling this positive just because the dog is getting faster. It's possible to have a negative acceleration and a negative velocity, which means that you would be getting faster in the negative direction. The reason why I know the acceleration is positive here is because I decided to call the direction of the dog's velocity positive. And if the dog is getting faster, that tells me the acceleration and velocity point in the same direction. And because velocity is positive, acceleration will be positive. So it's going to move that way for 3 seconds. And the displacement the dog covers is going to be 20, and I know that's positive 20 because if it's moving in the positive direction, it's going to cover a positive displacement. And I want to know what velocity it started with, so I'm looking for u. I'm now going to use the steps of the guess method to finish this work. The SUVAT table takes the place of the givens and the unknowns in the guess method. I've already filled in my givens and my unknowns, so now I just need to identify the equation and then solve and substitute. So to find an equation, I'm looking for a kinematics equation that has S, U, A, and T, the things that I have, the thing that I need, and nothing else. Looking at my equations here, I can see the only one that has S, U, A, T, and no V is the second equation right here. So I'm going to take that second equation and put it in my equation section right there. So that's the equation that I'm going to use. I'm now going to solve the equation for U. So just writing this out, I can see that u by itself is going to be equal to s over t minus 1/2 a times t. Finally, I'm going to substitute, plugging in my values, solving for u. This gets me 3.7 meters per second. So 3.7 meters per second is my answer to the problem. It's the initial velocity of the dog. So if you want to move 20 meters while accelerating at 2 meters per second for 3 seconds, your starting velocity absolutely has to be exactly 3.7 meters per second. So the thing that physicists like about the kinematics equations is that this doesn't just apply to this one situation. This holds true for literally any moving object in the universe. To make these other things work, to give you that displacement, that acceleration, and that time, you need to also have that exact starting velocity. So it doesn't matter whether we're talking about a dog or a car or a planet or an asteroid or literally anything, the kinematics equations will always apply and give us that same answer. Going on to example number 2, a ball is rolling up a hill at 10 meters per second, but gravity is causing it to slow at a rate of 1.5 meters per second squared. The ball is accelerated by gravity until it is moving at 5 meters per second down the hill. How much time did this take? Diving into step number 1, we need to identify one direction as positive and the other as negative. So this time we do have 2 directions. We have up the hill and down the hill. So I'm going to consider up the hill to be positive and down the hill to be negative. And again, if you chose opposite signs for the direction, you would still get the same answer at the end. So in step number 2, kinematics equations can only be used if the acceleration is constant over the motion they are predicting. And here I can see that I still have just one constant acceleration. This ball is just being constantly accelerated by gravity at this rate of 1.5 meters per second. So I'm going to skip step number 2 because that doesn't apply here either. So in step number 3, we're going to be filling in that SUVAT table, identifying an equation, and solving and substituting. So I'm going to go through. I can see that the starting velocity is up the hill at 10 meters per second. So I'm considering up the hill to be positive, so I record that number as positive. The acceleration is slowing it down, and again, negative acceleration doesn't necessarily mean that the object is slowing. The reason why I chose acceleration to be negative here is only that if it's slowing down and it has a positive velocity, acceleration must point in the opposite direction as the velocity, because slowing means the acceleration is working against the velocity to make it slower. So acceleration must point in the opposite direction as the velocity, so if the velocity starts positive, the acceleration is going to be negative. So that's why I know the acceleration is negative, not necessarily because it is slowing, but because it is slowing and the starting velocity is positive. We know that this acceleration continues to apply until the ball is moving at 5 meters per second down the hill. So down the hill I've defined as negative, so I have to record that 5 meters per second as negative 5 meters per second like this. And we want to know how much time this took. So just to clarify, what's happening here is that this ball is going up the hill, slowing to a stop with a negative acceleration, and then the negative acceleration continues to apply after the velocity is at 0 when it's stopped, and it begins to make it faster and faster in the negative direction. So that's another reason why the final velocity is negative here. So by the time the final velocity comes around, the acceleration, that negative acceleration, is causing it to move faster and faster and faster down the hill, because the negative acceleration is adding to the negative velocity to make it more large in the negative direction. So I need to identify my equation and then solve. Looking at my equations here, the only one that connects u, v, a, t, and doesn't have s in it is the first equation right here. So that is going to be my equation. And now I need to solve for t. And this is what t is going to be. And now I just need to substitute. And when I solve this out, I'm going to get 10 seconds. You'll notice that the units perfectly cancel out 2 seconds. So that means this is going to take exactly 10 seconds for the ball to change its velocity from positive 10 to negative 5. This is the last example, number 3. A car is accelerating from rest at 5 meters per second per second. It does this for 10 seconds before it stops accelerating and drives at a constant velocity for 4 seconds. It then slows to a stop at a constant acceleration in 6 seconds. What total displacement did it cover? So here, I can see that we actually do have 3 different accelerations. There's an acceleration where it's speeding up, there's an acceleration where it has a constant speed, and there's an acceleration when it's slowing down. So I have to split this up into 3 different kinematics problems. So this is step number 2 actually being used. You have to split up the problem into different sections where each section has one constant acceleration. So instead of writing out the steps and the equations, I'm just going to show you how you would solve each part of this problem. I can see that the acceleration in the first part when it's speeding up is 5 meters per second per second. And in the second part, it's just moving at a constant velocity, which means that the acceleration is 0. The velocity isn't getting bigger or smaller in that time. There's 0 change in velocity if there's a constant velocity. And when it's speeding up, it's taking 10 seconds altogether, and it's at a constant velocity for 4 seconds. And this last period of motion is going to be 6 seconds. It says that it starts from rest, so in the very first part of its motion, its starting velocity is 0. And the final velocity at the very end of its motion is also going to be 0. It's slowing to a stop in those last 6 seconds. My rule is that if I have at least 3 kinematic variables, I can always use them to solve for a 4th kinematic variable. So in that first section where they're speeding up, I can plug those 3 into a kinematics equation. In this case, it's actually going to be v equals u plus at to solve for the missing variable. So I can use that equation to find v is equal to 50 meters per second. I'm going to skip the math there just because I want to show you the overall structure of this problem. And because this is the final velocity of its speeding up phase, if you think about it, that's going to be the starting velocity of its constant velocity phase. So it's going to start the period where it has constant velocity with the same velocity that it ended with when it was speeding up, because it's speeding up and then moving at a constant velocity. So the final velocity speeding up is the starting velocity when it's constant. So that's going to be 50 meters per second. And using kinematics, I can see that this is also going to be 50 meters per second, the final velocity. And because that's the final velocity in the constant velocity phase, that's going to be equal to the starting velocity when it begins to slow down. So I'm really just piecing together whatever information I can, and as soon as I fill a SUVAT table with at least 3 variables, I can use those 3 to solve for other variables on the table. So in that first situation, I can use my SUVAT variables to find the total displacement is 250 meters. Plugging in my variables in the second section gets me a displacement of 200 meters. And now that I have all 3 in the last section too, I can solve that too and find that that displacement is 150 meters. So that means the total displacement is going to be the 3 displacements added together, which is going to be 600 meters. So that's how you would solve a kinematics problem involving multiple different accelerations. You split the problem into multiple parts, make connections between each part. In this case, the final velocity of one is equal to the initial velocity of the next. And anytime you get at least 3 kinematics variables, you can always use those 3 to solve for a fourth in the same table.